Good day. We continue our lecture on design of shafts, and today's lecture is lecture number 34. Today we will take up the design of the shaft for the fatigue loading, and in the last class you have seen that we have already learnt about the design of the shaft based on ASME code. So, to start the design of the shaft for fatigue loading, you see that we again come down to the familiar diagram of the stress amplitude and mean stress diagram, what we have seen in our earlier class. Here you can see the three sets of curves, one representing the Soderberg line, another representing the Goodman line, another representing the Gerber line, and this A is a point where whose stress amplitude is represented as sigma A and mean stress is represented as sigma m. You know that the Soderberg, in the Soderberg criteria, the material property is the yield point, whereas in the Goodman and Gerber criteria we utilize the material property as a ultimate stress, whereas for the fatigue loading property we have the endurance limit. Now, if we look for the familiar equation, that we can write down these equations, which is again a repetition of the equations what we have already seen in the earlier lecture. So, Soderberg criteria is given by sigma amplitude by this is the endurance limit, sigma mean stress, yield point equals to 1 by factor of safety. Similarly, the Goodman criteria is given by this expression, and the Gerber criterion is given by this expression, the third expression. Now, these expressions are quite common to you, and the next one, if we look, then you can see that this is the expression when we consider the situation of combined normal and shear stress, and here we are considering the Soderberg criterion only. As you know that in case of the ductile material, we multiply the stress amplitude by the fatigue stress concentration factor Kf. This is a fatigue stress concentration factor Kf, and similarly in case of shear we use a fatigue stress concentration factor for the shear. Now, here this particular equation, this expression is just written in another form by multiplying both the sides of this equation by sigma yield point, and we get a equation of this nature where this particular component is important. The important lies in the fact that this sigma yield point by factor of safety can be called as what? It can be called as simply an allowable stress or the design stress. So, one can conclude that this entire expression, which is equivalent to the design stress, will be nothing but somewhat an sigma equivalent. So, what is the idea? That means, if we can find out this value of the sigma equivalent, so this sigma equivalent will be containing the terms of the design parameters, and that if we equate with the material property, then we get the desired design situation. Similar is the case for the shear stress equation, where the shear yield point is multiplied on the both sides of this equation to give a expression of the equivalent shear stress of this nature. So, this is primarily we are writing down as in this shear stress equivalent, and this shear stress yield point by factor of safety is nothing but the design stress. So, this idea will be taken up for getting an equivalent normal stress or a equivalent shear stress. Now, if we come down to the next slide, then we see that if we use a maximum shear stress theory, then what we get? The tau max equals to tau allowable, nothing but the design stress, and that with the usual expression is that sigma equivalent by 2 whole square plus tau equivalent whole square. So, it is needless to mention that once again this tau equivalent will contain what? It will contain all the terms of the stress amplitude, the mean stress and the material properties. So, this expression once we write down in the forms of tau equivalent and sigma equivalent will be the terms containing all the design parameters what I told you just in the earlier slide. And just like the maximum shear stress theory, if we try to look at the distortion energy theory, then also we know this expression of distortion energy theory comes off with this particular form, and if we substitute the values of sigma 1 and sigma 2, then it can be shown that this expression sigma y by factor of safety will be sigma allowable, and that will come out to be as sigma equivalent square plus thrice of tau equivalent square. Now, here what is being done is that this sigma 1 and sigma 2 values are replaced in terms of the values of the shear stress and the normal stress acting onto the element. Means what is the idea is that if suppose we are having an element, we know that if it is acted upon by an sigma, it is acted upon by an tau, for which we can find out from the Mohs circle. Okay, that means if we plot for the Mohs circle, what will be this sigma 1 and this is a sigma 2. So, this sigma 1 contains these terms of sigma and tau, and that if we in this present case we are expressing this as equivalent, tau also as equivalent. So, if we substitute these values in sigma in this particular expression, or in other words that sigma 1 contains these values, and so if we substitute sigma 1 and ultimately the form will come out to be of this nature. So, in this case either we can use maximum shear stress theory or we can use the distortion energy theory for the design of the shaft. Normally what happens that most of the designers opt for the maximum shear stress theory, because as we have seen it is a more conservative compared to the distortion energy theory. But anyway, the choice lies for the both the theories. Now, this is a design based on the stiffness. So, prior to discussing the design based on the stiffness, let us make a concluding remark on the design of the strength. So, as far as the design of the strength are concerned, you have seen that we have only utilized the basic stress equations what we have learned in the earlier lectures, and those strength theories were nothing but one was a semi-core design, another was the design for fatigue, for which we have used the Soderberg criteria. So, as long as the design of the shaft based on strength is concerned, we will be treating the subject in two ways. That means, either we can use the ASME design code or we can use the just Soderberg criteria for the fatigue loading. It depends that how the design data are provided to a designer. So, based upon that, one has a choice of choosing either of the two theories what we have just learned. Now, we come down to the idea of the design based on stiffness. Now, what is a design based on stiffness? A simple situation we can conceive like this, that suppose you are walking over the corridor of your institute and that is the first floor. Now, when all of you are walking over the first floor, just imagine a condition that the entire floor is just swinging when you are putting your steps. It is not breaking, but it is just having a swing. So, how do you feel? So, that is the idea. That means, what is happening by virtue of putting a load. Suppose I take up this particular one and that is the floor over which you are walking. Now, if you are walking down and every time the floor swings, means it is just having a flexibility. So, it is just swinging like this. So, that is sometimes in the design is not desirable, or in other words, that when a load is there, the two things are to be satisfied. That one thing is that it should not break. It should not break, that particular part we have already covered, that is the design based on strength. At the same time, if the requirement is that it should be stiff enough so that the deflection is limited, then we call the design is based on stiffness. So, when we consider the design is based on stiffness, two things comes into picture. One is just by applying a bending load, this particular beam or this particular machine member, if I consider, will bend, but the bending should be limited to a certain given limit. If this machine member is applied upon with a twist, then this machine member will of course twist, but up to a certain limit. So, that limits are normally set by the designers, and considering those limits, one can set the dimension of the machine element, and that is in short what we call as a design based on stiffness. So, here we first consider the fact that is called the lateral stiffness. So, what is the lateral stiffness? That means, if we are considering some machine member, some machine member, okay, such acted upon by some support and a load is there, then it will have a natural tendency to bend by the action of the load, and this particular deflection, well, just let me draw a clear one. So, that means, if this is the machine member, it has got a deflection like that under the action of load, say P. Then one has to limit this deflection. So, that is the stiffness criteria. So, the requirement for such design is this, that one has to determine the maximum shaft deflection delta, and how? Using any of the methods that are listed below. One is a simple integration method, one is a moment area method, another is the energy method. You have you are quite conversant with these three methods in your earlier course, and so I do not go to details of these methods. However, the main idea is that using either of these three suitable method, one has to find out the deflection of the shaft. And normally what we do, if there are series of loads acting onto a shaft, thus creating the lateral deflection, then what we will do, you will try to search out for the maximum deflection occurring onto the shaft due to the various kinds of load which is responsible for creating the lateral displacement. That means, a shaft acted upon by various loads will have, say, a deflection pattern very exaggerated. So, here it is like that, this is like that, this is like that. So, we understand that this is the maximum deflection which is occurring. So, if we can find out this deflection and design with a certain limit, then of course, it will be satisfying all other conditions. Now, in this case, we consider the design in summary like this. Delta is a function of applied load or loads, material property, moment of inertia and length of the machine element. From this expression of moment of inertia and known design parameters, including the deflection delta and shaft dimensions, can be obtained. That means, this is the basis of the design. That means, you find out this deflection as we have discussed earlier. Now, you know the moment of inertia will come into picture. Moment of inertia means the geometrical dimensions will come into picture and other design parameters like load etc., will come into picture, and the shaft dimensions thus can be obtained if we choose a suitable limit for delta. Now, coming down to the next slide, we find an example. What is this example? A simple beam acted upon by a load P at the central location. So, here we can find out that what is the maximum deflection. So, obviously, the maximum deflection will be occurring over here, and when we find out this maximum deflection, we know the basic equation for this deflection delta is PL cube by 48 EI. So, that we find out this value of DI, where you know the I has been, this I has been replaced properly by the value of what, you know that value of I will be in case of a circular bar. Here we are considering a circular bar by d to the power 4 by 64, and that if we consider over here, then you get the desired diameter. Well, if it is a rectangular section, obviously the dimension or the cross sectional area of the rectangular section could have been found out in the similar manner. So, you can see this deflection, this particular dimension of the shaft depends upon the load, depends upon the length, depends upon the material property, and this is the delta max what you should prescribe. So, according to your design, you set a value of delta max, so that with all other known parameters a shaft dimension can be obtained. In the similar manner, if we consider the torsional rigidity, then we see that the torsional rigidity means what? Means basically we know the angle of twist, what will happen to a machine member by application of a load like torque. We get a angle of twist which is commonly given by this expression TL by GIP, you know all these things, and if it is expressed in terms of degree, then a form of like comes into this fashion. Here again the expression has been written for a circular member. Well, so this IP can be for a circular member, can be for non-circular member like rectangular section, etc. But here, just to have a continuity of the entire shaft design, here the expression has been written in the terms of a machine member having a circular cross section. So, in a similar manner, what happens that let me first give this notations: theta angle of twist, as I told, L length of the shaft, and G is the shear modulus of elasticity. Now, coming back to the idea that what is this particular limiting value of theta? The limiting value of theta is normally 0.3 degree per meter to around 3 degree per meter, depending upon, say, for machine tool shaft to the line shaft. Obviously, you understand that the rigidity of a machine tool shaft is very important in consider to the line shaft, because if a machine tool shaft is not rigid enough, then what will happen by the application of the cutting tool? Then it will have, obviously it will have a deflection, and that deflection will cause what? It will cause a material, I mean the job which you are turning will be erroneous in as far as the dimensions are concerned. So, that is the reason, depending upon the application of the shaft, where you are going to apply, I mean where you are going to use the shaft, one has to set for the value of the theta, means the what is the allowable angle of twist one should tolerate. Now, this value of 0.3 degree per meter to 3 degree per meter is just a guideline. So, you please note that this guideline has been provided to you to have an just a thumb rule idea, but it is no way a fixed value, and one has to change these values depending upon his requirement. So, this actually ends the ideas of the shaft design based on the stiffness. So, based on the stiffness, we see that we are just utilizing the bending equation and the equation of torsion, in particular the angle of twist, just to find out the design, find out the shaft dimensions. So, here we see that the design of shafts requires two ideas once again to just speak out. One is based on strength, another is based on rigidity. So, I think you are clear about these two design aspects. Now, once you have designed a shaft, taken into account either the strength criteria or the stiffness criteria, or maybe both, but anyway I would like to say that in the case of the stiffness, the shaft dimensions obviously are going to be much higher compared to what you will get if you consider the strength criteria. This is a general rule. Now, after a design the shaft, one has to look into this aspect also. That is what has been given here as a note on critical speed of rotating shafts. You know that what is the critical speed? The critical speed of a rotating shaft is the speed where it becomes dynamically unstable. Now, what is that particular speed? So, in terms of frequency, we can say that it is very common, or it can be shown that a frequency of free vibration of a non-rotating shaft is same as its critical speed. This particular part already you have done in your earlier vibration courses. So, I think we need not go into details of this particular aspect, and moreover this is beyond the scope of this class. However, we know the frequency of free vibration of a non-rotating shaft is the same as critical speed. So, we find out the frequency of free vibration, and that will be the same as the critical speed. So, if we look to this aspect, the equation of fundamental or lowest critical speed of a shaft this is a typical case when it is placed on two supports, is given as F critical. Okay, this is the F critical. So, here you please note that the expression has been represented in terms of frequency than the speed or the rotation. So, this is here is the expression where this W1, W2 etc. are the weights on the rotating bodies, and delta 1, delta 2 are the deflections of the shaft due to the respective weights of W1, W2 etc. So, what this specify what this implies in actual practice could be a gear, could be a pulley, and so on so forth. And corresponding to the gear, you are having a deflection delta 1, corresponding to the pulley you are having a deflection delta 2, which are the known parameters, and from there you can find out the critical frequency of the shaft by this formula. But one thing is there, this particular formula has been derived using these expressions. Please have a look. The assumptions are like this: the shaft is weightless, which is a very major assumption. The weights are concentrated, bearings and supports are not flexible. This is very important because none of the supports are really rigid, they will be having an flexibility. So, that incorporates some additional deflections, and with that particular point, and again with the above these two, number 1 and number 2 points, one need to get an accurate formulation other than what has been displayed over here. Anyway, as a first design aspect, one can use this equation what has been given here very easily and find out the critical speed. Look, the shaft operating speed should be well above or below a critical speed value. This is obvious, otherwise you know the resonant frequency will occur and the shaft may have a failure. In the similar manner, the number of critical speeds are there, and that depends upon the number of rotating bodies. As many as critical speeds will be coming into picture, as many rotating bodies are there onto the shaft. So, this requires the frequency will be normally that fundamental frequency is being considered, but one can also look into the all other frequencies, whether it is creating any sort of danger during design or not. Anyway, the basic concept or the basic idea is something like this, that a check on the critical speed should be done to avoid any sort of resonance failure of a machine member. So, this one is a design check, one can talk in this manner. Now, let us consider a simple problem. The problem is stated well if you look at the this figure. So, what is this one? A shaft supported on two bearings over here. A pulley is there having a weight of 1000 Newton. Pinion should have some weight but not specified, and these dimensions of the shaft etc. are given over here, and this pulley is acted upon by belts whose tensions are 1000 Newton and 4000 Newton respectively. But now for normally for actual design, one has to find out from the idea of belt drives that what should be the tensions actually acting onto the pulley. Next, this particular pulley will be rotating a pinion, and the pinion in terms will be rotating a gear. So, gear forces coming over the pinion has been given here for simplicity, and these are given as 2200 Newton and 6000 Newton respectively. So, if you look into the particular problem, you see one thing is that this particular shaft is getting a loading, one from this side, another from this side. Okay, that means one in this particular plane and another into the transverse plane, in the perpendicular plane. So, we require to find out what will be the bending moment onto this particular, while we consider the loading on this plane, and similarly while we consider the loading onto this transverse plane. So, this particular requirement first has to be followed, and then we can find out the design. By the way, just look at this, the pulley diameter is 400 mm and pinion diameter is 200 mm. Just this distances are 200, 400, 200 respectively. So, this is the loading as well as the bending moment diagram. Now, if I just go back to this slide, then please note that the torque applied onto this particular shaft will be obtained by this 6000 Newton multiplied by this radius of this particular pinion, or we can find out 4000 in minus 1000 multiplied by the radius of the pulley. So, here we can use either of these two to find out the torque, and incidentally the torque is constant over the shaft. Now, if we look into this diagram, you can see very well that the pulley weight, if this is one is a vertical plane, another is a horizontal plane. Well, what I was telling, that is pulley weight of 1000 Newton will be in the vertical plane, and as it is given as 1000 Newton directed downward, and the gear force acting onto the pinion is an upward direction. So, this is the loading as far as the vertical plane is concerned. Now, if you consider the horizontal plane, then you can see the total pulley force was 1000 and 4000. So, combined the 5000 is coming like this, and the gear force onto the pinion in this direction was 2200. So, both are coming as downward, whereas here it is one downward and it is upward. So, if we look into this one, then in the vertical plane the bending moment diagram is given is this manner, and where the maximum value of bending moment is occurring at the D and given by the value minus 850 Newton meter. In the similar manner, onto this particular horizontal plane, the maximum bending moment is coming at C as 860 Newton meter. But if we consider the resultant of the two bending moments of the vertical plane and the horizontal plane together, then obviously by inspection we can find out that this resultant, that means at the point D, the bending moment will be more compared to the bending moment what we are getting at this particular point C. So, if we consider that fact, then what we can see is that the bending moment here will be how much? It will be coming out to be, I just use this location to write. So, 580 square plus 850 square and square root of that. So, that comes out to be, well, I just giving you the value as 1029 Newton meter, and this value will be utilizing as a maximum, and that is the moment at D. Now, what we can see for the given data, we can see that the design of the shaft, design the shaft for minor to heavy shock loads. So, with the given data, we think, we can see that the design will be based on strength, because nothing has been told about the stiffness, and if we consider the design based on the strength, then we find that ASME code will be the most suitable over here, because we do not know anything about the fluctuating components. So, if we consider the design based on ASME code for the minor to heavy shock load, if we just look at the various factors to be utilized, then you will be finding out that CBM can be well taken as 2 and CT, the factor for torsion, can be taken as 1.5. So, we come down to this particular slide from where we know the bending moment was 1029. So, let us solve the total problem. So, what we find is that torque can be written as how much? It is 200 multiplied by 4000 minus 1000, and the unit will be coming out to be Newton millimeter. So, this comes out to be 600 into 10 to the power 3 Newton millimeter. What is the bending moment? Bending moment, which was maximum at AMD, came out to be 1029 Newton meter. So, that is equals to 1029 into 10 to the power 3 Newton millimeter. So, if we use the ASME code, then the design comes out to be this is D0 cube will be equals to 16 pi into sigma design, means allowable or whatever we can call it, into square root of Cm into m is 1029 square. So, let us bring out this 10 to the power 3 outside, plus Ct into (600) square. So, Cm is 2.0 and Ct is 1.5. What is this value of sigma design? This sigma design we can consider as 40 megapascal. Why? Because ASME code suggests that it can be 56 AMPA for the shafts without any shaft keyways etc., and 40 MPa if it is got a keyway. So, of course, the pulleys and pinions will be attached with the keyways. So, we consider this to be the value for the material property. So, if we consider all these values, then a simple calculation will show you that this value will be coming out to be 65.588 MPa, and that approximately 66 mm. Why? Because if we look at the standard sizes of the shaft, then this should be 66 mm. So that it specifies a standardized values. Now, in this case, you see one thing, that while doing these calculations, once again to repeat, that you always consider these ideas. So, before I just talk about, so I think we are confident that this value of D0 is coming out to be 66 mm. So, our problem is solved. So, for the given problem, the shaft size should be 66 mm. Anyway, I have considered the simplest values like that the shafts are solid, it is not hollow like that. So, many combinations could have been done in this particular calculations. You could have taken some other values of cm and ct also. Anyway, whatever I was just trying to talk about is that while doing these calculations, once again just to repeat, it is very important that you always take the force in Newton unit, dimensions in millimeter unit, and stresses and related parameters in MPa, that is Newton per millimeter square unit. So, this will make your life very simple in the sense that you do not have to unnecessarily think of changing over to the units every time. So, this gives you the idea of how you are going to design a shaft. Now, one of the important feature of the shaft in design is that the bearings. Now, what we understand that the shafts will be mostly rotating bodies, as we have seen in our earlier discussion, and these rotations are possible through the bearings. So, as because the bearings and shafts are so closely related to each other, one also should have some knowledge of the bearings that are normally utilized in the design. So, we are not considering any separate lecture course or a lecture chapter on bearing. Rather, in this particular shaft, we are just giving a brief overview of the bearing. So, this particular bearing ideas are the main theme of this particular lecture. Now, if we consider this idea, then we do have largely two types of bearings. One the fluid film bearing, another are the rolling contact bearing. The fluid film bearing categories are journal bearing, thrust bearing, slider bearing, etc., where you will be having the entire load of the shaft are being carried by a fluid film, and another category is called the rolling contact bearings, which are categorically are the ball bearing and the roller bearings. Now, these are very common, you have seen, and also you must have seen the bearings like journal bearing and thrust bearing. So, these are the two types of bearing one normally use for their designs. Now, first of all, let us have a very quick comparison of bearing friction. because the friction is one which will be always there, and one has to look to be a friction to reduce the frictions in the bearings, and so that the operations are much more smooth and power loss is less. Now, if we see a plot of the friction versus this is the shaft speed, then you can see for the lower shaft speed, somewhere here lower shaft speed, you can see journal bearing are having more friction compared to what you get the roller bearing and the ball bearing. That means ball bearings are do not have do have a very small amount of friction, then comes a roller bearing, and then comes a journal bearing. So, that is sometimes the ball bearings and roller bearings are also sometimes called as anti-friction bearing, but it is not exactly anti-friction, but still people call it. Anyway, we will be seeing the interesting part from this side. When the shaft speed increases, you see this ball bearing and roller bearing frictions phenomenically increasing, but the journal bearing friction is relatively low in that particular case. So, that means what is happening, as because the shaft speed increases, then obviously the journal bearings are more acceptable compared to what we get for the ball bearing or the roller bearing. Now, there are of course some advantages and disadvantages as far as the friction is concerned. We need not discuss, you can just see from this figure. And other situations, something like that, this ball and roller bearings are relatively costly, it takes a little bit more space, and it requires also the seats to be manufactured over the shafts, so that the bearings can be properly fitted over there. But this bearings had one of the good advantages, that low friction at the low shaft speeds, relatively low shaft speeds, and the maintenance of these bearings are also relatively easier compared to what journal bearings. Okay. Now, however, the journal bearing can take up and huge load. Of course, these also can take up huge loads, but journal bearings are mostly suited for very high speed and high loads also, and it takes lesser space and little compact. Now, we start with the idea of the journal bearing. So, this we can consider to be that if you look at this one, then this is the housing or the main bushing rather you can say, and this is the shaft which is placed within this bush, and this one is called actually the journal. This blue one is sometimes it is called as the, this is the journal. Now, this one you can see is that when it is at rest, then you can see that the bearing load will keep the journal in contact with the bush at this point, and this light blue color is nothing but the filled up oil or the lubricant, what you can say. Now, whenever the journal starts rotating, then what will happen at the low speed conditions, it is a low speed conditions, what will happen that with this load acting over the journal, the bearing has got a tendency to just go over here, because what will happen that if it is rotating onto this one, onto the bearing, a frictional force will come into this way. So, the orientation of this journal with respect to the bush will come out to be in the some way, so that this angle is basically the angle of friction. So, it will be the angle of friction, that means this particular friction force component of this load will be just balancing the friction force in this particular line. So, along this line there will be a balance of this friction force and the load component. And if there lies some amount of oil, then this amount of oil won't be very thick. In what I mean to say, that in this particular case almost a metal to metal contact will be prevailing, and some sort of oiliness or something will be there if it contains the oil, as I told you. If there is no oil, then there will be a purely metal to metal contact, and in case of the oil presence there will be just an oiliness, not the entire journal will be just lifted up by this oil. Now, when it goes to a higher speed, at a high speed, then what happens, that this oil field, this particular oil what is being over here, will have a continuous film. You can see there will be a continuous film which will be created over here, and this continuous fluid film will be generated in this zone. And if you consider this zone from here to here, you can see the passage is something like an converging one. So, whenever there is this type of converging zone, then there will be an oil film having a minimum thickness over here will be created, and this oil film can take up an extensive load, as it is being shown in that exploded view, that if there is a converging zone and an oil is over here, as I have shown you, and if this particular one is moving with respect to this, then you can see that it will be generating a pressure profile over here, and it will create an load bearing capacity. So, the summary of this idea is that to build up a positive pressure in a continuous fluid film to support a load, a converging zone is necessary, and that is what the concept of journal bearing. So, what is that one? That if it is at rest, it is just having a contact over here, no fluid contact, only metal to metal contact. At this zone, there will be mostly a metal to metal contact, a very thin layer of oil, something we can call as an oiliness is present over there at a low speed. Whenever the speed goes higher, then you will see a continuous fluid film having and converging and the diverging zone. Now, as a matter of fact, these diverging zone, what you can see over here is actually will be responsible for creating a negative pressure. So, sometimes this oil, due to the negative pressure over here, can be drawn into this passage due to this converging to diverging zone, where it creates a negative pressure. So, this idea is given, this idea is the underlying fact of the journal bearing. Now, this is based on what we call as the hydrodynamic theory of lubrication, and this was first seen by Petrov in 1983, where he did that experimental investigation, and that showed the dependence of this friction on viscosity of lubricant, load and dimensions of the journal bearing. So, this is the first man who conducted that experiments, extensive experiments, and Tower in the same year 1883 and later also carried out some experimental investigations on bearing friction, bearing film pressure. So, he took out this experiment looking onto the some aspects of this particular experiments by Petrov. So, the experimental investigations of Petrov and Tower are the background of development of the hydrodynamic theory, and which later was given a mathematical shape and in the form of well known Reynolds equation due to Osborne Reynolds in the later years, who found out from the experimental investigations the interesting results, and which he put into the form of a mathematical equation of the hydrodynamic theory. So, we continue of more onto the overview of the bearings in the next class. Thank you. Good day. We continue our lecture on design of shafts, and this is lecture number 35. In the last class, we have been discussing about the hydrodynamic theory of lubrication. So, what in short I have written hydrodynamic theory. And just a recapitulation that this particular hydrodynamic theory, the historical background is that from the experimental investigations of Petrov and Tower and looking at their interesting results, what happened that Reynolds suggested a general equation for the hydrodynamic theory, and this equation is given here. As you can see, this equation is nothing but purely a flow equation under the pressure gradient, and that is for the left hand side, and the corresponding right hand side is some sort of device or some sort of pressure generation mechanisms that we will talk about. In this particular equation, what has been assumed is that the lubricant is incompressible, and the wedge shaped what we have been talking about earlier has been assumed to be a somewhat a straight profile. Okay, this is the wedge if we consider, and this is the